Is it visible now?
Yeah.
Okay. Okay, so we'll discuss about K0 to exact categories. I don't know what else has already been covered in this series, but so exact, yeah.
Basic definition was given, but it's better that you start fresh. K3 of Wallhausen categories and K3 of monoidal categories has been covered so far.
All right. Okay. So today mostly the topics is K0 exact category. So what is exact category? Let me start with what is exact category, and then we'll see. So basically, before the exact category, there are two kind of categories that's called more important. This is called abelian category, and another is called additive category. Okay, so first category is called additive category. That is very basic. If you want to do some kind of homology theory on this, I think you should start with additive, then you have to go to abelian. So abelian category is designed in such a way, such a way such that so that you can do homological algebra. Okay, so that you have a Cardinal Category notion and also chain complexes and all these things. And additive category is a very, in the sense of very simple settings. It has only, it's a category which contains zero object. So what is zero object? Zero object means it must be a terminal and both initial object. That means terminal means for every object in a category, you should have a map from this object to that terminal object. And initial means from every object, from this initial object to every object, there is a unique map. For example, in the category of ring, set of integers, actually you can think as a initial object. All right. And also, it's closed under finite product. Okay. That means if you take the product of two object of this category, you blend with the same category. And another important is home set has an abelian group structure. Is abelian group. Okay, so for all AB. And the third one is, and last one is, and the composition is bilinear from A to B. So this is a bilinear. So this is a definition of additive category. So what are the example of additive category? First example is all, of course, any abelian groups. One can check all those properties instead in the settings, and but which is non-example. So category of fields. All fields. Why this is not additive category? Because it doesn't have initial object. Because field homomorphism already depends on the characteristics. So it has no, not abelian, not additive. Because it has no initial object. Okay, all right. And what is the abelian category? Okay, I'll come to the definition of abelian category, but basically abelian category is a kind of a nice category where you can do all the homological variables. You have a cardinal, co-cardinal notion, and you have short edge sequence notion. But sometimes what happens in K-theory, abelian category expectation is too much actually. So somehow you have to find some middle path. So basically, exact category is a in between something, roughly. So exact category is a halfway house between abelian and additive. So additive category has a very less information, but abelian has too much information sometimes. So that's why you need something, you need more flexibility in K-theory. So that's why you need in between some category, which is exact. And roughly, this is a roughly, you can think abelian actually exact plus additive. So additive category with some extra structure, you can, what you get, that is actually behaves like abelian. Okay, so I will come to the abelian category, then we will define what is exact category. So basically, exact category is a category in between abelian and additive category. It's a halfway apart between abelian and additive category. And we'll come to the definition of exact category in details and with the examples. Okay, so far so good. So what is abelian category? Abelian category, just quick recall. So it's an additive category, first of all. An additive category. A is abelian if for every map A is a cardinal coefficient. So that means whenever you have a map between two objects in the category, the kernel and co-kernel must be in the same category, lie in the same category. Okay. So this is the first condition you need. That means the give you existence of kernel co-kernel. And for a short edge sequence, that is the first requirement. You need a kernel and co-kernel, right? To define a short edge sequence and to define a edge sequence concept. And second thing is every monomorphism is the kernel of its co-kernel. And third is every epimorphism is the co-kernel of the kernel. See, I cannot define everything in details, but at least with some example, I can explain what is the meaning of all this. So first of all, example again, the abelian groups, regular abelian groups in abelian category. Because kernel, if you take a group homomorphism, it will be the kernel, it's again a group, if it's the abelian group. But if you look at the just only group, category of only groups, need not be abelian, then this is not abelian category. Not abelian, right? Because if you consider any subgroup of a group G, then the axiom 2 is failed. It's not a kernel of its co-kernel unless the H is normal sum. So, but when you consider category of abelian groups, then you are safe because any subgroup is a normal in this case. So that is the difference, kind of a property 2 and 3. And what is the more interesting example in our settings now? Mod R category of R modules, where R is a ring. Yeah, I think it's better to come out ring here. Okay, this is also abelian category. You can check all the thing because kernel and kernel also have a model structure naturally. But you can consider subcategory MR. This is a category of finitely generated I module. So this is a subcategory of model, but is not abelian in general unless R is noisy. Because if you look at a map between two modules and if you look at the kernel may not be finitely generated unless R is noisy. So in general, it's not abelian unless R is noisy. Okay. So this is the example and one example of abelian. All right. But we'll see later on the category of this category is very interesting. The category of finitely generated R module or category of coherent OX module for schemes X. So similarly, MX, you can given a scheme X. Is a category of coherent OX module. In the same region, this need not be a abelian category unless it's in original schemes. Okay, but K theory of this category is also but interesting. This is called the G theory. Okay. So as you already mentioned that K theory of symmetric monodial category has been discussed. So there is also notion of K theory abelian category. But in K theory abelian category, the problem is the following: if R is not Nigerian, then you cannot study K theory of MR kind of thing. Okay. Okay. So now we come to the exact category. So definition is bit notational, but if you don't understand the definition, don't worry, but only just work with the examples. So start with the additive category. A is an additive category. And also the category of projective module, I think I forgot to, that's also important, like PR. Category of finitely generated projective R modules. Okay. So is this a symmetric modular category? I think you have already done that. This thing.
Yeah.
Yeah. Because PR, you know, category of finitely generated projective R module is a symmetric modular with respect to the direct sum. That has already been discussed, I believe. Okay. And then you can also consider the K theory of this category because under the direct sum, this has monodial structure. So you can take the group completion to get the K groups. All right. Okay. So this is also important category for us. Okay. So now basically additive category. Exactly. So a kernel co-kernel pair in a additive category A is a pair of composable morphism such that I is a kernel of P, and P is a co-kernel of I. Okay. So I is a kernel of P means what? That means P compose I is 0. So that is the definition of kernel in category theory. I believe all of you know. So actually very difficult to explain everything because then it will take actually 5-6 lectures. All right. So basically, so suppose you fix a class of kernel co-kernel pair. Suppose a class of kernel co-kernel pair in A is fixed. Suppose you consider all kernel co-kernel pair in the additive category A. Then we say I is admissible, monic, if for I there exists a P such that IP belongs to this class, and additional epic is defined dually. That means given a P, there exists I such that I comma P belongs to this class kernel co-kernel pair. Okay. So there is the immediate remark. In an abelian category, a sequence is shortage sequence if and only if this and P, I comma P is a kernel co-kernel. So note that in abelian category we have a right notion of kernel, co-kernel, so we have a notion of a shortage sequence. But in exact in general additive category, you really don't know about the kernel co-kernel whether they exist or not. So you just that's equivalent to the actually shortage sequence in the settings of abelian category. So basically, this kernel co-kernel pair is a generalization of the shortage sequence. From this remark, you can see, and you can check. Okay. And second thing, so this is always a kernel co-kernel. For all AB belongs to A, for A is additive category. So that direct sum sequence is always the kernel co-kernel pair. In fact, these are actually shortage sequence always in, this kind of map. So this is always a kernel co-kernel pair for any additive category. Okay. So basically now we will focus on the kernel co-kernel pair. As long as we do not know whether the kernel co-kernel exists in the category, now we focus on the kernel co-kernel pair actually. So that's basically generalization of the shortage sequence. In abelian category, the kernel co-kernel pair actually coincides with the shortage sequence. All right. Okay, so now we'll focus on this kernel co-kernel pair and we'll define an exact category. So basically, exact category means you have to give some exact structure on an additive category, so that actually it behaves like a abelian category. All right, so what is that exact structure. So let be a class of kernel co-kernel pair that is closed under isomorphism. We say that epsilon is an exact structure on an additive category A if it satisfies the following. The following example. Okay, so what is the first reason? Yeah, so identity always a admissible monic. So that means additional monic means what? It means there exists a p such that p dot identity comma p must be in this class, and that is always that is expected. Your identity always isomorphism, right? In the setting of everywhere, identity is isomorphism. So it is also part of the shortage sequence, right? And second thing, this is also admissible epic. E3 is the class of admissible monic is closed on the composition. Can make composition up to additional monic again, additional monic. Same thing for epic. Class of all admissible epic is also closed under composition. And E5B says that the push out exists along any. So the definition says the following. The push out of along any arbitrary morphism always exists. Suppose take any additional monic and take the push out along any arbitrary morphism. Then this resulting things, what you get, that is also additional monic. The push out of additional monic is additional monic, and push back of a additional epic is always additional epic. Okay, these are technical things. So basically, exact category, what is that? Exact category is an exact category is a pair A comma epsilon where is an additive category and is a class of kernel co-kernel, which are closed under Rashomon and satisfy E1 to E6. So E1 to this is E6. Okay, so this is the exact category. So start with the additive category, then you will put a exact structure on it by considering a set of all class of all kernel co-kernel pairs which satisfy the certain properties, the 6 properties. Okay. So note that an additive category may have a different exact structure. It's not that there is a unique exact structure. For example, any additive category always admits an element. Okay, so another one, an element of is called a short edged sequence. Okay. So any element of the epsilon is called the short edged sequence. Basically, the kernel co-kernel pair, as I already mentioned, this is the generalization of short edged sequence. So if your category is abelian, then the element of this epsilon is anyway the short edged sequence. So now we call this is a short edged sequence, the kernel co-kernel pair. So what is the first example? An additive category may have a different exact structure. So one trivial exact structure is the following. An additive category A always admits an exact structure by considering epsilon to be the class of sequences isomorphic to that I defined just the split edged sequence. If you consider all split edged sequence in the class of kernel co-kernel pair, then it's one can check this definitely satisfy all these 6 properties actually, and that's a trivial exact structure. If you only considering that your epsilon just split things actually, then this is the exact category. So this is trivial exact structure. Okay, but there may be another exact structure, but this is a trivial exact structure you can always put on an additive category by considering the all split edges or this kind of system, which is isomorphic to this thing. That is basically the split. And second example, any abelian category can be given an exact structure by defining epsilon to be the class of usual short edged sequence. So in abelian category, you always have a notion of a short edged sequence. So just consider the all short edged sequence in this class, epsilon class. Then you say, and all those property will satisfy the E1 to E6. So any abelian category is an exact category. Okay. So any abelian category always an exact category by considering the usual edges, short edged sequence. Okay. So in particular, abelian group, category abelian group, mode are both are exact. So exact category means it's an additive category with some exact structure. So whenever the structure is clear, then we just write it is exact. Okay. So note that the mod R is an exact category because it's an abelian category. So an abelian category always be exact category by considering this whole set of all classes. An abelian group in the same region. All right. So now there is a lemma, but I'm not going to prove it. The lemma is the following. The lemma, let M be a full additive subcategory of an exact category N. Assume that M is closed under extension. In N, what does mean that? So closed under extension means given in a short-edged sequence, for every short-edged sequence, if A and C belongs to M, then B belongs to M. So that means closed under extension. Okay, if A and C belongs to M, then B has to be belongs to M. Okay, so think about a category of projective module, MR, where first and last one is actually projective module. Then direct sum of projective module again a projective module, right? So middle one has two projective module. Okay, so that if A and C are in M, then B has to be belongs to M. So this is the closed under extension in N. Okay, and this sequence in N, because N is the exact category, right? So it has a class of kernel co-kernel pair. So this, and as I said, that kernel co-kernel pair is said to be short-edged sequence in this setting. So for this short-edged sequence in N, so that is closed under extension definition. Okay. Then this lemma says M is an exact category with an exact structure inherited from N. Okay, so basically the exact structure of N basically induce the exact structure of M on the subcategory under this condition. Suppose M is a closed under extension. Okay, so what are the immediate consequence of these things? That MR and PR both are exact. So what is MR? MR is a category of finitely generated R module, and PR is a category of finitely generated projective R modules. Why they are exact? Because both are sitting inside in mod R, right? And mod R is an abelian category. Any abelian category is an exact category. So basically, it's a subcategory of an exact category, and definitely this is a closed under extension, because whenever you have a short exact sequence like that, if first one and the last one is a finitely generated, then middle one has to finitely generated. Similarly for projective. So it's a closed under extension. MR and PR both are closed under extension in mod R. Okay. So with this lemma, MR and PR both are exact category. But remember that MR need not be abelian category, and PR need not be abelian category unless R is. MR is only abelian category if R is non-abelian. But here at least they are actually exact category. Is that okay? So far so good. We have already considered the K theory of this PR. This is also example of exact category. But in the settings of exact category, definition little bit different. But of course, in the case of PR, everything wins. All right. So okay, now also the exact category. Now we can consider the category K theory of exact category. So what is the K theory of exact category? So the diversity group K0 of an exact category and is the abelian group having one generator for each isomorphism class of objects in N and a relation whenever there is a shortage. In N. Okay, so basically it's a free group generated by every object, assuming class of object modulo that is relation. Whenever you have a solid sequence, it just it's given by this relation. Okay, is the definition clear? So now, as I said, that PR is actually category. PR is actually exact category. So that's actually given by K0 of R. So K0 of PR actually given defined as K0 of R, K0 of B. Think PR as an exact category. Okay. Now look at PR is also a symmetric modular category under the direct sum, right? So there is another notion of K0 direct sum PR. If you think K0 as a PR as a symmetric modular category, you can also consider the K0 by group completion, right? So that is also, so this should same. These two things should be same. Why? Because in PR, every shortage sequence splits. Note that this kind of things actually vanishing. This kind of relation is actually automatic in category of PR. Every shortage sequence vanishes. So taking a group completion or by modeled by this relation actually doesn't matter. So these two things are coincident. This is actually simple exercise you should try to do it actually. So if you think PR as a symmetric monoidal category, you can consider the K0 in terms of group completion because PR has a monoidal structure under the direct sum. So you can take the group completion, that's the K0 of R. If you think as a symmetric monoidal category. And another also PR, you can also think as the exact category, and then you can also use this definition, what I just gave. And these two definitions coincide because in PR, every shortage sequence splits. So in general, so let's definition first. A split exact sequence and split exact category N is an exact category in which every shortage sequence in the epsilon is split. So example, PR is a split exact. Okay. And so let N be a additive category. Sorry, exact category, but any exact category is also additive, right? And it's also a finite product. Let's say yes. Okay. So any additive category with this finite product is a monoidal structure. You can think as any additive category can be think as a symmetric monoidal category. So you can also consider this K0 of this, that means group completion, and also K0 of n as an exact category. These two things have to be same. So that means for a split exact category, n taking the group completion method and taking as an general definition coincides for an only split exact category. Otherwise, these two groups actually differ. Basically, one of the otherwise K0n is the question of K0 of. Otherwise, K0 of an exact category can be thought as a question of a K0 of symmetric modular category modular some relation. Okay, but in the setting of split exact category, these two definitions coincide. So, as I said, in PR is a split exact category, so both are group, both K0 group are coincide. Whether you think as a exact category or you think as a split exact category, it doesn't matter. Symmetric modular. Okay, but in a exact category, whenever there is a solid sequence which is not split, then maybe you can get a larger K groups. Okay. And also, I think this is also very good exercise in scheme theory for any schemes X, VBX, category of vector but analog is not splitting. Okay, so then K0 of X is defined as K0 of VBX. And category of vector bundle over scheme X is always the exact category with the same region, because if you think as an if it's sitting inside category of OX module. Okay. And then you have a suppose X is Noetherian. And then consider MX, category of coherent OX module. And that is a K0 of, you can also think as an exact category. Then it's called a G0F, G theory. This is called the G theory. So K theory of a coherent OX module is called the G theory. And K theory of a vector bundle is called the basically usual K theory. Okay, so one of the main result in this direction for K theory exact category, that when this K theory and G theory actually isomorphic. So there are, you get the two groups, right? When these two groups are isomorphic. So that is this theorem is called the resolution theorem. That is I am going to discuss today. But in more general setting, as a consequence, we will get this. Okay, so the resolution theorem. So let M be an exact category. And rho be a full additive subcategory. That is closed under M. Suppose also that these two properties for any exact sequence if P and P double prime belongs to rho, then P prime must be belongs to. So that property is called the closed under kernel. Okay, that means suppose P and P double prime belongs to rho, then P prime must be belongs to rho. Okay, and second property is called every object of M has a finite resolution by objects of rho. All right. So if you consider if you consider rho is PR and M is MR. Now think in back of your mind, you should think PR and MR. So M is MR and rho is PR. So MR is category of finitely generated module and PR is category of finitely generated positive module. Okay. So note that this first property is satisfied always. MR is the exact category, as we have already seen. First one is also satisfied because whenever you can this exact sequence you can think as an exact sequence in MR. Whenever this one and this one are actually positive, then P prime must be positive. This is an exercise in commutative algebra, right? Because in this sequence it actually splits, then P prime must be positive. And every object of M has a finite resolution by object of P. When this is true, that is not always the case, but every object always has a resolution, right? Because category of module actually enough projective. We will always have a resolution, positive resolution, but there is no guarantee there is a finite resolution. So for that, you really need a condition on R, which is called a regular. The condition is called regular. So whenever R is a regular Noetherian ring, then the second property always works. Okay, if R is regular Noetherian, then every M belongs to MR has finite projective resolution. But this is actually for general category theory. Every object of M has a finite resolution by object of rho. But in this case, rho is PR. Okay, so then in the case of regular Noetherian ring, these two properties holds for PR and MR. Now this theorem says the following. The theorem says then the inclusion functor M induces an isomorphism K and rho isomorphic to K and M. So this is true for all higher K groups also, but today only I discuss the K0 part. In the next talk we will discuss the higher K3. Okay. So that means in that case, K0 of rho isomorphic to K0 of M. So if you consider in our settings that PR sitting inside MR, provided R is regular Noetherian, okay, then the theorem says that K0 of PR same as isomorphic to K0 of MR, which is nothing but a G0 of R, as I discussed. So in that set, K theory and G theory actually isomorphic in the case of regular ring, or in general in the case of regular scheme, regular Noetherian schemes. So basically, in the case of non-singular variety or non-singular schemes, actually the K theory and G theory has no difference. They are same actually, but for the singular case, they are different. They are different. Okay, there may be difference. So this is the important consequence of this theorem. This is called the resolution theorem. Okay, that for the regular Noetherian ring, K theory and G theory coincides. And because G theory has a very nice properties. For example, G theory is a homotopy invariance. And so that for regular ring, K theory is also homotopy invariance. All those. Okay, so we'll discuss sketch of this proof and then I'll stop. So, but this is the theorem, I think, due to Quilling, but Quilling proves a more general theorem. And as a consequence of this general theorem, you get the resolution theorem. This theorem due to, I think, Quilling, that let rho is sitting inside M, where M is exact, and this is closed under extension. And then satisfy two properties that for any exact sequence in M, if P is in row, then P prime is in row. So note that this is a closed under kernel. This is more stronger than closed under kernel. In the closed under kernel, actually, we demand these two things are actually row, then P prime is row. But here, actually, only this, if P is in row, then P prime is row. So the second property is for any M in M, there exists a P in row and P, there is apimorphism, or better to write this. Okay. So from then Kn of rho is isomorphic to Kn of M for an M category. So this is a more general. Why this is more general? Because if you look at the condition on these things, every object has a finite resolution. The second part. But here I am saying that if given any object in M, we have a epimorphism from P to M where P belongs to rho. Now suppose the second property says the following, that given any P, you have a epimorphism. Now look at the kernel. What is the meaning of kernel? The kernel, by first property, that kernel must be in row, because this is belongs to row. Right? So that means every element of every object of M has a finite resolution. The second property also satisfied here in this setting also. All right. So that's why this is more general. Actually, if you prove this theorem, then your first theorem was actually consequence. Okay. So how to prove this theorem? The sketch of proof. Okay. So that always induces a map, right? K11. Because by sending object like P to P, and you know that I is always exact function. Inclusive factor is always exact function. So that also preserves the relation. If you want to define a map in the level of K0, what you have to do? You have to define a map between the free abelian group. Then you have to, that map should respect the relations also, right? That induces a map in the level of K2. But this I is actually exact factor, right? That means exact sequence tends to exact sequence. So that means actually this, basically this functor actually respects the relation. So basically that induces a map from K0 row to K0 n. Now I want to define inverse map. Okay. How to define that thing? So given M belongs to M, there exists a P belongs to rho, such that, as I told you, that there is a epimorphism. And then if you look at the kernel also, so that is also belongs to rho by part 1. So basically, given any M belongs to rho, there exists an exact sequence. So now define sending any M to P minus P prime. Because given any M, you have always have a sorted sequence by object of rho, P prime and P. So you're just sending this thing. Now what I have to check? That we have to check phi is well defined. Want to check phi is well defined. We have to check this M. The resolution is independent of choice of the independent resolution, right? So that means we have to check P of M is independent of the choice of resolution. Because given any object M, you may get another resolution, right? The Q prime, Q and Qm. So that we have to check that it must be independent of the choice of resolution. So that is the more technical part. Otherwise, it's clear that this map is actually. Otherwise, it's clear that P is actually inverse of the I star, right? Clearly, P is inverse of I star because P minus P prime always in M and K0M. Because of this relation, whenever you have a shortage sequence, that always actually splits. That is the relation in the K0 group, right? So that's why the M always can be written as P minus P prime. So basically the P actually inverse of I star. So that means which implies actually I star is an isomorphism. But how to check this well defined? So only technical parts to check the well defined. So that is basically in the case of module, this is basically called as Zanuel lemma. You can check this lemma in the stack project. I can actually maybe tell 003, I give same point. You can look at this. What is said that in the case of ring actually, but for the category, the proofs are of duality. So are we a ring? M belongs to mod R. Suppose there are two short edge sequence. With Pi belongs to positive module, then K direction P2 isomorphic to L direction P1. So which means in the K3 class P1 minus K same as P2 minus A in K0 class. That's what you want to check, right? Check the well definedness. Because M is given by suppose P minus P prime and Q minus P prime. That these two class must be same. So that is what you want to check here. So this is a consequence of this lemma. And that's basically just a diagram chasing on this. Yeah, probably I will stop here today. Maybe next time I will discuss the higher K3 analog using some recent technique. Okay. All right.
All right. So are there any questions? Well, if none, then let's thank the speaker. So we'll meet next week once again at the same time.
Maybe. All right.
Yeah. Yeah.
So next week maybe the same result we will prove. Basically, we'll discuss the proof for higher category how it's doing. Okay.
All right.
Or maybe some consequence in law and polymerase. How much to pay
Okay.
All
Yeah.
right.
Thank you very
Okay,
much
then
for the
I'll-
lecture, and thank you everyone for being here. And
Oh.
just share the notes with me.
Oh, I don't have notes, open notes actually.
No, whatever you wrote today in the screen.
Okay, that helps.
Yeah.